In this video, we'll discuss how to summarize, describe, and compare data distributions. Now, the first distribution we'll discuss is the uniform distribution. This is where all the entries have approximately equal frequencies. They don't have to be exactly the same, but when you look across, they're all relatively the same. For example, here, this could be like a six-sided die, and it's been rolled, and you can see all those rolls over a large number of times is relatively equal. Another common distribution is the symmetric distribution, where the left and right half are approximately mirror images of one another. They don't have to be exact, but they should be relatively close. We can also have skewed distributions. This is where there will be a tail to the graph that's going to elongate more on one side of the graph than the other. We can have a negatively skewed distribution where the tail is on the left, so it's extending to the numbers on the left, whereas a positively skewed tail extends to the right. And you think about positive and negative, where's the tail going? With a negative, the tail is going towards the negative numbers. With a positive, the tail is going towards larger positive numbers. So it's all about the tail of the graph. Now we can also have a bimodal distribution. This happens when there are two locations that may have larger frequencies than anywhere else in the graph. And often we'll use the mode with this to explain what's happening. Now, some of the other optimal measures of central tendency occur when we're looking at the symmetric and the uniform. We want to use the mean. And when the data is skewed, we're going to use the median because the skewed data is being impacted by those outliers that are creating the tail. So if we look at this current graph on the left here, we'd say this is positively skewed. There's a tail going to the right. So because it's skewed, we would want to use the median. In contrast, this graph is relatively symmetrical. And since it's symmetrical, we'd want to use the mean. Now, we can also calculate percentiles, which when we order our data, the percentile will represent the percent of the data that is at or below a given value. So say we have Becky who took a test and scored an 88% on the test. In comparison to all students who took the test, 74% scored an 88 or lower. So it's important to understand the difference between these values. The 88% is the score Becky personally scored on the test. The 74th percentile, or that 74% that scored 88 or lower, represents that percentile for Becky. So she scored more, as well as 74% of the people that took the test. Now, when we hear the word quartile, we're looking at very specific percentiles. This is where the data is split at the 25th percentiles. So we're looking at the 25th percentile, the 50th percentile, and the 75th percentile. And that 50th percentile, because the data is ordered, will represent the median. And that's a helpful piece to understanding how to find the other quartiles. So if we want to determine all three quartiles, we first order our data. We determine the median because that will give us the second quartile. And we know we've done it correctly if what is remaining for our data is the same size on the left and right of our median. And they have to be the same amount of entries on the left side and the right side of the median. Then we will determine the median of the lower half, which will be the first quartile, and the median of the upper half, which will be the third quartile. Lastly, often when we determine our quartiles, we will also state the interquartile range, which is where we take our upper quartile, the third quartile, and subtract the lower quartile, the first quartile. So say a store was counting the number of customers that came in from 8 a.m. to 9 a.m. during the last 15 weeks. So here's the data. It is in order. If we wanted to determine the quartiles, we'd first find the median. In this case, the median would be 15. It is the middle number in this ordered set. And that will represent Q2. That allows me then to draw a line right through it, and if I look, the left side and the right side will both have 7 numbers on them. That will allow me then to find the median of the lower half. So the middle of this one would be Q1, which is 10 customers. And if I look at the upper half's data and find its median, it would be 18. And there I have my 3 quartiles. And then my inner quartile range would be 18 minus 10, which would be 8. Now I can use this data then to help me construct the Box-and-Whisker plot. And this is a way to represent the quartiles as well as how much our data ranges overall. So when we construct the Box-and-Whisker plot, we first order the data. We then find what's called the 5-number summary, which is the absolute minimum data point, the absolute maximum data point. Then we're going to find our 3 quartiles, and those are the 5 key points we need. We create a number line or a horizontal scale that will allow us to put tick marks and place each of these numbers equally spaced from the minimum all the way up to the maximum. We're going to plot the 5 numbers above the scale, not on it, above it. We draw a box around Q1 to Q3 and a line through Q2. And then we're going to draw whiskers out to the maximum and minimum points. And our graph should look generally like this. We have our box around Q1 to Q3 and a line through Q2, and then our whiskers to the minimum and to the maximum. So say we go back to the data we just had. We know the 5 points, the minimum, the maximum, and then Q1, Q2, Q3 we already determined. Because we want to plot every single point on the number line, we will need a number line that goes from 5 to 37. We want to make our graph as accurate as possible to understand what's happening with the distribution of the data. So we plot our 5 points. We draw a box around Q1 to Q3 and a line through Q2, and then we draw out our whiskers. And there, that will create the Box-and-Whisker plot. Now, another distribution we commonly will deal with is called the normal distribution. This is when we have relatively symmetric data, and when you plot it, it will form something that looks very close to what's called the bell-shaped curve. The nice thing about the normal distribution is that the mean, the median, and the mode are all equal to one another, and they will represent the 50th percentile, which means half our data is below the mean and half of our data is above the mean. Now, within the normal distribution, we can actually split up our data based on the standard deviations. And when we hear that word standard deviation, we're talking about a measure of how spread out the data is from the mean. If we talk about one standard deviation out, approximately 68% of the data will fall in that category, being one standard deviation below the mean to one standard deviation above the mean. And because it's symmetric, that 68% gets split in half. 34% below, 34% above the mean. When we go 2 standard deviations out, we're now at 95% of the data will fall between 2 standard deviations below and 2 standard deviations above. 68% is here, which then leaves us with 27% to split between the 1 and 2 standard deviations. So 13.5% on the bottom and 13.5% on the top. Additionally, we can go out another to the 3rd standard deviation. So we're pretty far away from the mean at this point, but almost all the data, 99.7% of the data, falls within 3 standard deviations of the mean when we're dealing with the normal distribution. That means a very, very small percent falls between 2 and 3 standard deviations below and above. But there's still even a tiny percent that goes beyond 3 standard deviations, which means that there's 0.15 of 1% beyond 3 standard deviations, both below and above the data. if we took all those percents together, they will add up to 100%. All of our data should be able to be represented on the normal distribution. Now, one of the reasons we have to pay attention to these standard deviations is we talk about the percentiles based on the standard deviations. If we want to calculate the corresponding percentile, we're going to sum all of the percentages to the left of a given standard deviation. So say that Monique scored 2 standard deviations above the mean on a national test. What percentile did she finish? Well, let's look at our bell curve with the percentages listed. We would draw a line at the positive 2 standard deviations. And then because we're looking at a percentile, it's everything at or below that line. So we're going to add up all of these values from left to right up until we hit our vertical line. That means we're adding 0.15%, 2 3500ths, 13.5, 34, 34, and another 13.5. If we add up all those values, we get to 97.5, which means that Monique finished in the 97.5th percentile on the national test. So being 2 standard deviations out means she's scoring higher than 97.5% of the population. Let's look at one other example to help. Say a child's height is 1 standard deviation below the mean for their age. What percentile is the child's height for their age? So again, let's start with the bell curve and the percentages. We're going to draw that line at -1 because we're 1 standard deviation below the mean. Then we're going to look at all the values to the left of the line. And we're going to add those 3 values together. So when we add 0.15%, 2 3500ths%, and 13.5%, we're going to get to a total of 16%. That means the child is in the 16th percentile for height for their age.